Hello coders, welcome to my video. In this video, we'll explain about an ABI and why it matters. Okay, so ABI is an application binary interface. So if API is how source code talks, ABI talks about the compile program, the binary level. So when we write a high level, code in .c file, the computer won't understand it. Okay, it will first convert into the machine language so that CPU can understand that in a zero and one forms. Okay, so ABI is a contract between a program and a library. So both program and the library is compiled independently. For example, we have lot of libraries in Linux. So when we compile our program, it will take that dynamic libraries and link to your program to resolve some APIs. Okay. So whatever code is there in the library that resides in the RAM as a memory footprint in the binary form. Okay. So it defines how these two codes can interact with each other without breaking, crashing. Okay. For example, there are various uh, things that ABI includes. Okay. So first one is a function calling convention. So when you call any library function in your C program, it will pass some arguments to that function, and that function got into the stack in the memory level. Okay. So when your program get executed as a program uh, so once your exe got into the RAM, your function got into the stacks during execution. At that time, your ABI comes into existence. Okay. So second part is a data type size. For example, we have integer for 4 bytes long as 8 bytes on a 64-bit Linux system. So ABI fixed the size of a type as well. Okay. So structure layout. Okay. For example, ABI defines how structure is arranged in the memory, how padding is done, and how alignment is done within the structure. So if any compatibility issue between a program and a library due to the structure layout, this will break your program at the ABI level, not in the API level, because the API level will compiler will give direct, you know, um, uh, error, but in the ABI level, it will give you problem at the runtime when your that function is being called. That is a part of the library. Okay, so we have binary compatibility as well. So if ABI changes, old program may crash even they compile fine. Okay, because now your old program is linked to the new library. So when you change the library version, your old programs don't know like what is under the hood. So when your program uh, executes at that particular time, when it hit the function, at that time it get to know, okay, this function have some problem in the library, and at that time ABI break happen or some crash will happen. Okay, so if there is a change in the system calls in the library level, at that time as well we got the ABI issue. Okay, so ABI also govern what is dynamic linking. Okay, so at the time of a dynamic linking of loading this shared library, this is also governed by ABI. So if anything changed in that layer, your program or your system got affected. Okay, so this ABI is there at the cross compiler level as well. Okay, because our GCC must follow the same API for the program as well as for the library at the same time. So If anything changed during the course of time, because these executable and the library are two different entities working together in your OS, so that should be taken care. Okay. And we have the ABI stability as well, that is guaranteed by the glibc. So if the ABI change, or your library function or version will change, that will break your old program. So these all things we should kept in mind. So this is the flow from your program to the OS. So in your program, you have function calls and data types. These all things will be go to this ABI layer, where there is a binary rule calling conventions. Okay. So that is a part of this library, and we have shared function and structure layout within this library. So anything changed in this library would directly affect your program and this OS as well. So let's take an example to understand this concept what we have studied. So here what I did is I just taken an add function. I'm adding 100 plus 200, and here I just taken one function add, and this function is defined somewhere in this libmath. Okay. So now I'll compile it. So I'll have GCC hyphen O, disabling the optimization, and then we have main.c, and we have libmath.c. Okay. And hyphen O, I have main dot, so compile it. Okay, it got resolved. So if you see here, I have integer as return type, and the parameters are int and int. Okay. So now what I will do, I'll inspect this binary now, main.out. So I have readelf hyphen s main.o, and I'll grep add. So here you see the address of the add where it is loaded. Okay. So here we have the address, then we have this function, the symbol of that function. Okay. Here we have this as a global function that is not there in this main, but uh, it's there in the other file. Then we have this as a default visibility. Okay. And then I have this add function here. Okay. The symbol name. The linker will resolve through this add. Okay. And this will show how your function is represented in the memory. Okay. So now what I will do, I'll do object dump, then I have hyphen d, then I have main.o, grep hyphen 8, then for example, and here I will do add. And once I do this, I got this function from this binary. So this, uh, you know, so this main.o have some assembly code. Okay. So this is the, near to the binary format, how the computer will understand these all things through the registers. Okay. So your add function will expand like this under the hood that machine can understand. Okay. So if you see here, we have 32-bit register. So these are 32-bit register EDI and ESI. So these are somewhere the first argument uh, of the add. Okay. So this is the second argument of your add function. Okay. So now here we are loading these things. Okay. And ex is a return type from that function. That is also an integer. Okay. So once this function got cleared, it will return your output. So this is the assembly footprint of your add function, and it's called from here. Okay. So right now we are using int and int using this add function, and returning is also int. So all the things are 32-bit. What if I change it now? So if change it to long and long. Okay. And now I have to change from libmath.h as well. So here also I will change long. Okay. Now I'll compile it again. Okay. Give me some argument issue, but that is fine. So if I do it again, okay, and now this one. So you have seen the registers are being changed. So earlier EDI, EDX are there, but now there are RDI that are 64-bit registers. So now your register is changed. So the memory footprint of your function got changed by changing uh, the data type as well. So the behavior may be different in this case. So why I'm talking about these all things are, so for example, if your library got changed or a new version is adapted for 64-bit and your application is not updated, because for updation you need to compile your application with the new library. Okay. So you will stuck in the ABI issue where your program got crashed at the ABI level. So in this video, I have told you what all are the things that got changed in the library that will make crash your program. So these things we should kept in mind while we are working with the ABIs. So let's see in the next video. Thanks.